Hello, this is Mr. Gilmore with the 4.1, the Triangle Exterior Angle Inequality lesson. Now, this is interesting because we'll technically talk more about triangle inequalities next chapter, chapter 5. But in order for us to continue into this chapter with some of the angle relationships we're going to look at, we do need to actually prove the triangle exterior angle inequality first. So in today's lesson, we're going to dive into what an exterior angle is, and then also look at what does this theorem actually hold for us. At the very end of the lesson, we're going to prove that this theorem is actually true. Let's start with what is the definition of exterior angle. So imagine then you're given any polygon. Specifically, let's talk about a triangle. If you took any one of the sides of that triangle and extended the side out, then what happens is there's an angle that's formed with that extended side and already a side of the triangle. We then call that an exterior angle. That exterior angle forms a linear pair with one of the interior angles of the triangle. In our example below, we've extended out the side of our triangle and formed an exterior angle of angle 1. Now, of course, at each vertex, we could extend out the sides in two different directions, which means we would actually form two exterior angles at each vertex. So any given triangle actually has a total of 6 exterior angles. Now, there's going to be another angle that we find with our triangle in relationship to that exterior. Each exterior has what we call remote angles. They'll specifically have 2 remote angles. So in this triangle, whenever we talk about an exterior angle, each exterior comes with 2 remotes. So let's then pick one of our exterior angles and look at what would the remote angles be. A remote angle are the 2 angles that are not adjacent to the exterior. In other words, they're the remaining interior angles that are not adjacent to the exterior. So depending on which exterior you pick, then also depends on what its remotes are. Let's look at angle 1 in our diagram below. Angle 1 is an exterior angle. So angle 1 actually has 2 remote angles, angle 4 and angle 6. It's adjacent to angle 5, but we want the non-adjacent angles. So angle 4 and angle 6 of the interior of our triangle are not adjacent. We can continue that pattern and look at angles 2 and 3 as our remote angles. If we look at angle 2, its remote angles are angle 4 and angle 5. Because it's adjacent to angle 6, we want the other 2 non-adjacent interior angles. Angle 3 then thus has angle 5 and angle 6 as remotes. There is a relationship between those exterior angles and their 2 remotes. This is what the relationship holds. We are introducing now the triangle exterior angle inequality, or to us, the TEAI. Here's what it states. The measure of an exterior angle of a triangle is greater than the measure of either remotes, meaning that in our last diagram, any one of the exterior angles we picked would always be greater than any of the 2 remote angles that it would be related to. Now, we're going to be using this diagram here to actually prove that this is true. So in our diagram, we have triangle ABC such that we've extended out our segment AC through point C to a point D, and we form an exterior angle of angle BCD. We're going to specifically prove that the measure of angle BCD is greater than the measure of angle B. However, before we actually jump into this proof, we are going to start off with a series of constructions. Let's take a look at what these constructions are. First, we take our segment BC, which is the side of our triangle, and we place a midpoint on it. We're allowed to construct midpoints. Let's call that midpoint M. Next, let's actually connect the segment from vertex A to the midpoint. So we connect A to M. However, that segment has a measure to it. We're going to then extend that segment through point M to a point Z such that the segment AM is in fact equal to MZ. Our last then construction is to take point Z and connect it to point C. What we've done is we've strategically created another pair of triangles, and what's interesting is we're going to find very quickly in this diagram with our constructions that we have a pair of congruent triangles, and using congruence we can then reach our conclusion that our exterior angle is in fact greater than its remote angles. So now let's begin our proof. With our new additions to the diagram of the constructions, we're going to have some information that we can actually use to reach our conclusion. Let's start with the information we can gather from our constructions. Already, I have BM is equal to MC because M was the midpoint. So I'll go ahead and, if we take a look in the diagram, BM and MC are equal to each other. We also know that AM and MZ are equal to each other by our construction. Notice then that there are two triangles here in which two sides of the first are equal to two sides of the second. Take a look specifically at triangle ABM and CZM. Those two triangles are provably congruent. Here's why. We already have two sides of the first equal to two sides of the second. Look at our pair of vertical angles there. So we know that the measure of angle AMB is equal to the measure of angle ZMC by vertical angles theorem, which then leads us into congruence. Triangle ABM is in fact congruent to triangle CZM by side angle side congruence. That means we open the door for our best friend CPCTE. But what are we looking for? Specifically, I'm looking at angle B this time. Angle B is now equal to a corresponding angle of that triangle we just proved congruent. This angle here, angle BCZ. So I know that the measure of angle B is equal to the measure of angle BCZ. So where are we going with this? Why is it important that we know those two angles are actually equal? Well, let's then take a look at our exterior angle. Our exterior angle, angle BCD, is actually the sum of two angles. Because CZ actually is on the interior of that angle, we find that the measure of angle BCZ plus the measure of angle ZCD, that equals the total sum of our exterior angle BCD by our angle addition postulate. Now, we always then know the whole is greater than the part, so I can declare that the measure of angle BCD is actually greater than the measure of angle BCZ by the whole greater than part theorem. So what's then the conclusion? Well, we just proved that BCZ, this angle here, is actually equal to our remote angle, angle B. So then by using substitution, we can then arrive to the conclusion that the measure of angle BCD, our exterior, is in fact greater than the measure of angle B, our remote angle. And there we have it, QED. We've proven the triangle exterior angle inequality. Now, technically, you may be asking, should we also show that angle BCD is greater than its other remote angle, angle A? Yes, we should, which is why on the worksheet you will do that. There's a problem on the problem set in which you will prove that BCD is also greater than angle A. You'll note that on the worksheet, it's another series of similar constructions in order to prove that BCD is greater than angle A. What you'll see on the worksheet then is you will duplicate this proof of TEAI. You'll have both BCD being greater than angle B and angle BCD being greater than angle A. With those two proofs, then we have the complete set. So that means the triangle exterior angle inequality is going to come in handy. What you'll then follow up with is using that triangle exterior angle inequality to answer a few questions before moving on into our next lesson, 4.2. If you do have any questions with this lesson, do not hesitate to email me. With that, be good and do good.